Today I'd like to go through the solution to this FE example problem with you guys. It puts together a few different concepts and takes a standard problem, finding the moment of inertia, and extends it. We're going to be going through the current version of the FE reference handbook, finding appropriate references, and just solving this problem step by step. So let's get right into it. Okay, so what we're looking for here is the polar moment of inertia about the centroidal axis of this bilaterally symmetric cross-section. What this term here means, bilaterally symmetric, is that if we place the coordinate system right here in the middle of this body, we'd be splitting it left, right, up, and down into mirror images. That means that the center of this body is aligned with the centroid. And shown here is the centroidal axis, which is what we're looking for the polar moment of inertia with respect to. Now, the first thing is that if you recall, J is equal to the integral of r squared dA. We also know that Ix is equal to the integral of y squared dA, and Iy is equal to the integral of x squared dA. What that means is that J is equal to the integral of x squared plus y squared dA. That's the definition of R, which is equal to the sum of I, y, and Ix. So what that gave me an indication of is that if I'm able to compute both Ix and Iy and I just add them together, then I'll be able to find J. Where could we find that information in the reference manual? If we go here to the static section, usually I click dynamics and then I scroll up if I know the problem is going to be moment of inertia related. And I'll scroll up a little bit more. Right here, I'm seeing moment of inertia. For the moment of inertia, I see polar moment of inertia, and I see that the sum of Iy and Ix is equal to J. So that's what we're going to focus our attention on. We're going to find the two moment of inertias about the x and y axis and sum them together. And our shape is made up of a few different rectangles. We have Ix here and Iy here. Now, it's an important distinction between Ix and Iy. When you're looking at Ix, what you have is a rectangle where the x-axis is horizontal. That base term, the term which isn't cubed, is always parallel to the axis of interest. Ix, the single term, is just the b because it's parallel to the x-axis. Iy, the single term, is the h, which is why it's parallel to the y-axis. Let's go ahead and put down those two references. So this one is on page 98, this one is on page 95, and I have their section headings. Let's start with Ix. Now, from the reference manual, we know that Ix is base times height cubed over 12. You want to try to save as much time as you can. So if the axis of your object isn't aligned with the centroid, you have to use the parallel axis theorem. We're going to try to avoid that and save as much time as we can. So we're going to pick shapes which are advantageous to us. For here, we're going to pick this shape as number 1, this shape as number 2, and this shape as number 3. Why did I pick those 3 shapes? Is because their centroids are all aligned. Their individual centroids are all aligned with the current x-axis. What that means is that if I was computing Ix of this shape, all I would have to do is simply add 3 moment of inertias. Ix would be, for the first shape, it's the base 4 times the height cubed over 12. And I know that there's 2 of these. 1 and 3 are identical. So I'm going to double it right here. I'm going to go on and compute the moment of inertia for that second shape, which is 8, which is the base, times 4 cubed over 12. If I go ahead and reduce this term, I get Ix is equal to 8 to the 4th plus 8 times 4 cubed, all of this divided by 12. We have what Ix is. Next, we need what Iy is. If we went ahead and gone with the same shape selection, you can see that none of the centroids are aligned with the y-axis. We have this centroid over here, which has a distance d away from the y-axis. What that means for us is that we're going to have to using the parallel axis theorem. We want to save as much time as we can, so let's pick different shapes such that the y-axis is always aligned with our shape selection. Let's instead go with, let's view this as an overall rectangle which has its centroid aligned with the y-axis, and subtract off the moment of inertia of these two smaller rectangles shown here. That's good for us because the centroid of all of those bodies is aligned with the y-axis. The middle centroid is this red dot right here, and the other two shapes have centroids which are here and here. Let's go ahead and compute the moment of inertia about the y-axis. That is, for the overall rectangle, base times 8 plus 4 is 16. Base times height cubed over 12. And then we subtract off the moment of inertia associated with those two other shapes. This base here is the total distance 8 subtracted by the thickness of this portion here, which is 4. So that means we have 4 remaining that we can split into this top portion and this bottom portion. This base right here must be 2. We have 2 of those shapes with a base of 2 and a height of 8 cubed over 12. What that means for us is that Iy is equal to 8 times 16 cubed over 12 minus 4 times 8 cubed over 12. Now that we have that, we're finally ready to compute J. J is just the sum of Ix and Iy, so that's going to be 1/12, because they both have a 12th denominator, 8 to the 4th plus 8 times 4 cubed plus 8 times 16 cubed minus 4 times 8 cubed. Compute J as 2944, and the unit of all of these was centimeters. Right, remember J was the integral of r squared dA. Centimeter squared and centimeter squared makes centimeters to the 4th. So this is our final answer. Let's go back to the app, select this answer, and we can see that we got it correct here. If you're curious about my app, please, the link is in the description below. Check it out. You can also see that for each of these questions that I have here, there are written out solutions. This is basically a detailed solution of what we just did, where you have the final answer shown below. I hope this video was helpful to you guys. If you want to see more content like this, please like and subscribe. I'll see you in the next video. Goodbye.